Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on group lecture number 55, in which I will discuss on Cayley's theorem. Firstly, we state Cayley's theorem statement. A finite group G of order n is isomorphic to a subgroup of a symmetric group. Symmetric group means permutation group. Now we prove this. Let G is a group containing elements G1, G2, Gn be a group of order n. Let small g belongs to group G, then by closure property G1, G2, comma Gn are elements of group G. Let Gi equal to Gj implies that by cancellation law Gi equal to Gj by cancellation law. Therefore, Ggi equal to Gga means Gi equal to Gj. Also, we may write I not equal to J, that is Gi not equal to Gj implies that Gi not equal to Gj. Therefore, G1, G2, comma Gn are n distinct elements of group G. Let Sn be a symmetric group on the set G1, G2, Gn. Let phi is a mapping defined on G into Sn such that phi Gi equal to here G1, G2, Gn, here Gi-G1, here Gi-G2, Gi-Gn. This is a permutation belongs to Sn. Here G and this is Sn. This is phi. This is number 1. Therefore, phi Gj equal to G1, G2, Gn, Gj, G1, Gj, G2, Gj, Gn. This is also another permutation, belongs to Sn. This is number 2. Since Gi, Gj belongs to G, implies that Gi operation Gj belongs to G by closure property. Now, phi Gi Gj equal to G1, G2, Gn, Gi, Gj, G1, Gi, Gj, G2, Gi, Gj, Gn. This is another permutation. This is number 3. Let F equal to a permutation G1, G2, Gn, Gi, G1, Gi, G2, Gi, Gn. This is a permutation, belongs to Sn. Since Sn be the symmetric group defined on the set G1, G2, Gn, therefore each element of Sn will be a permutation defined on the set G1, G2, Gn. Let this is number 4. From 1 and 4 we get F equal to phi Gi. This is number 5. Now let H equal to a permutation here G1, G2, Gn, here Gj, G1, Gj, G2, Gj, Gn. This is a permutation, therefore it belongs to Sn. This is number 6. From 2 and 6 we get H equal to phi Gj. This is number 7. Now FH, F is a permutation and H is a permutation. Therefore, their product, that is composite mapping FH, is also a permutation. FH is a permutation on the set G1, G2, Gn. Here we write G1, G2, dot, 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 Gn. Here FH image of G1, FH G1. Here FH image of G2, FH G2, dot, dot, dot. Here FH image of Gn. Implies that FH equal to here G1. Now here FHG1, FHG1, here G2, here FHG2, dot, 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 here Gn, FHGn. This equal to here G1, here FHG1. Here HG1 means image of G1 is GJG1. GJG1. Here G2, FHG2, image of G2 here. H image of G2 is GJG2. GJG2, dot, 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 Gn. Here FHGn. H image of Gn is GJGn. GJGn. Since HG1 equal to GJG1, HG2 equal to GJG2, dot, 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 HGN equal to GJGN. This equal to here G1, FGJG1. Since F image of G1 is GIG1, F image of G2 is GIG2, dot, dot, dot. So F image of GJG1 is GIGJG1. Here G2. Now F image of GJG2, we write here GIGJG2, dot, 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 dot. Here Gn. F image of GJGN, we write here GIGJGN. For F image we write first GI. Here F image first we write GI, GI, GI. This is number 8. From 3 and 8 we get right side of 3 and 8 be same. Therefore, left side will be equal. Phi Gij equal to left side FH. This equal to F means in 5 phi Gi and H means in 7 phi Gj, using 5 and 7. That this is number 9. From 9 we get that phi is a homomorphism. This is number 10. Since car phi equal to x belongs to G such that phi x is identity permutation. This belongs to Sn. I be the identity permutation. This is number 11. Since identity permutation I equal to, here we write G1, G2 dot Gn. Here also we write G1, G2 dot Gn. This is number 12. Since phi x equal to, we write here G1, G2 dot Gn. Here xg1, xg2 dot xgn. This belongs to Sn. This is number 13. Implies that phi x is the identity permutation I equal to G1, G2 dot Gn. Here x G1, x G2 dot xgn. Here identity permutation is G1, G2 dot Gn, G1, G2 dot Gn, left side, and right side is G1, G2 dot Gn, and here we write xg1, xg2 dot xgn. This is number 14. Comparing both sides, we get G1 equal to xg1, G2 equal to xg2, comma dot Gn equal to xgn. Here G1 equal to xg1, G2 equal to xg2, and Gn equal to xgn. Implies that here G1 equal to xg1, G2 equal to xg2 dot Gn equal to xgn. This means x is identity element. of group G. Therefore, X equal to identity element of G. This is number 15. Therefore, from 11 and 15, we get phi, kernel of phi. Here X equal to only identity element. So here we write only identity element of group G. This is number 16. From 10 and 16. In 10, phi is a homomorphism, and in 16, kernel of phi contains only single element, identity element of group G. Therefore, from 10 and 16, we get phi is 1-1 mapping. This is number 17. Range of phi equal to phi of group G. This is 18. Since phi is a homomorphism, therefore phi G is a subgroup of symmetric group Sn. Since phi is defined on group G and phi is a 1-1 mapping, therefore number of elements in range phi is equal to number of elements in group G. Therefore, order of group G equal to order of range phi. Implies that order of G equal to order of phi G. This is number 19. Since phi is a 1-1 mapping, defined on a finite set G, and from 19, order of G equal to order of phi G. Therefore, phi is onto mapping, defined on G into phi G. Here this is G, and this is phi G. This is number 20. From 17 and 20, phi is 1 1 on 2, define on G into phi G. Therefore, phi G into phi G is bijective. Since phi is a homomorphism from 10, therefore phi is a bijective mapping and homomorphism. Therefore, G is isomorphic to phi G. Since phi G is a subgroup of symmetric group Sn, therefore finite group G is isomorphic to a subgroup of a symmetric group. Proved. We have two notes. Note 1, a subgroup of permutation group which is isomorphic to finite group G is called a regular symmetric group or regular permutation group. Here we have phi G is a subgroup of permutation group Sn, and this phi G is isomorphic to group G. Then phi G is called regular symmetric group or regular permutation group. We have note 2. In note 2, we have given the generalized version of Cayley's theorem, which is as follows. Every group G is isomorphic to a subgroup of the group of all permutations on G. Here it is not necessary that G is a finite group. G may be any group. Then this group is isomorphic to a subgroup of the group of all permutations on G, group G. Now we solve a problem. Problem is find the regular permutation group isomorphic to the multiplicative group G. G contains elements 1, -1, I, -I. Let F1 be the identity permutation on group G. This is 1, -1, I, -I. Here we write again 1 minus 1 I minus I. This is the identity permutation. Now F2. F2 is obtained by multiplying all this image by firstly minus 1 multiply 1 minus 1 multiply minus 1 minus 1 multiply I minus 1 multiply minus I, and this is equal to 1 here minus 1 here minus 1 here 1 here I here minus I here minus I here plus I. This is F2. F3 is again we write 1 minus 1 I minus I. Now we multiply all the image by I multiply 1 I multiply minus 1 I multiply I multiply minus I, and this is 1 here I here minus 1 here minus I here I here minus 1 here minus I, this is 1. F4 equal to, here we write 1 minus 1 I minus I. Now we multiply each image by minus I multiply 1 minus I multiply minus 1 minus I multiply I minus I multiply minus I, and this equal to here 1 minus 1 I minus I here minus I here minus minus plus I here minus I multiply I square minus 1 and minus 1 here minus minus plus I square equal to minus 1. Therefore phi G equal to a set containing F1, F2, F3, F4. This is the regular permutation group. Isomorphic to G, group G. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.